Okay, so in the, I tried to incorporate in this title the topic, central topic of this symposium, and I'm also using the words engineering and science, and I'm taking the larger sense of those terms, the larger sense of engineering, and the larger sense of what science is, and I want to apply it to our thoughts and needs about software. Viewpoints Research Institute is a 501c3 nonprofit public benefit organization. So we don't have a product. We're not trying to sell you anything. Brad invited me here to provide some alternative points of view on how we might think about software and how we might make software. Because the time is going to be dear, I put my email address up there. I should put it at the end, but I'll put it here so that if people have a question that didn't get answered while I'm here, I welcome email. I like email. I love it better than almost any other form of communication because I can decide when not to use it. You all know what I mean. Okay, let's tackle engineering first. One way of thinking about engineering is that in the world we're presented with situations. Here's a really nice, beautiful one, but it has a couple of drawbacks from practical human need that gives rise to an idea. We design something, we make a thing that caters to that, and if we don't extract principles from this thing, then we're not doing engineering yet, we're just tinkering. Tinkering is kind of the thing that is built into many mammals. If you have a cat, imagine what a cat would be like if it had hands. It would be basically a monkey. You would come home from a vacation and your house would be dismantled. So we want to extract principles, we want to push them back into the things. So we start doing principled building of things. Those principles leak back into how we design things, and they even leak back into how we have ideas. And so this has been going on a lot longer than mathematics and science. And in the 20th century, one of the ideas it gave rise to was a really, really tall building done very quickly. Here's what it looked like when they got done with it. And I'm not going to spend a lot of time with this, but when you talk about engineering, this is one of the 3 or 4 things that comes up is the Empire State Building. So here's an article in one of the engineering magazines that says, planning and control permit erection of 85 stories of steel in 6 months. And it wasn't just 85 stories of steel, it was 85 stories of steel and granite. And here's what it looked like. Here's the site after they demolished the old Waldorf Astoria Hotel. And then bing, 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 bing. And so they clad the thing as they went up. And the entire building of the Empire State Building took less than 12 months and was done by about 3,000 people. So we could not muster 3,000 people to do something major in less than a year in computing. So whatever we mean when we say software engineering, we don't mean real engineering. We mean something that we're aspiring to. And this is the way the term software engineering was intended back in the 60s at the Garmisch Conference in 1968, where it was coined, was an aspiration. Today, if you go to a university or many companies and ask them what is software engineering, they'll say it's what we're doing. That is manifestly not the case. And there's some really interesting things. So anybody who aspires to being an engineer of any kind should be intimately familiar with how this was done. And what's wonderful is there are many good books about it, including this facsimile of the foreman's notebook. One of the foremen every night typed on his Pica typewriter and took a picture and pasted it in there, and this has come down to us, but we don't know who the foreman was. And a few years ago, it was facsimiled into a book that you can buy. And there are many interesting things in there. One of the questions that was asked the aspiring contractors was, what tools do you have for this job? And one of them was Paul Starrett, who was one of two Starrett brothers. And they had built some very large buildings in Manhattan previously. They were one of three big companies bidding for this job. And Paul Starrett, and they'd all said to this question, well, we have all the tools we need and blah, 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 blah. What Starrett said is not a blankety-blank thing, not even a pick and shovel. Gentlemen, this building of yours is going to present unusual problems. Ordinary building equipment won't be worth a damn on it. We'll buy and make new stuff fitted for the job. That's what we do on every big job. It costs less than renting secondhand stuff, and it's more efficient. Okay, now in software, a first-order theory that's obtained as long as I've been in the field, which is 50 years, is that you should never build your own tools. It's a black hole. Don't build your own operating system. Don't build your own computer, for God's sakes. Don't build your own programming languages. Get all this stuff from the vendors. And that way you're actually going to speed up your ability to produce the thing that you want to do. Now, it turns out this isn't true. Or it's true if you don't know how to build your own tools. You can certainly get into a black hole. We all know of them. But in fact, the second order theory is also true, which is if you know how to build your own tools, then you better, because you can bypass not just the workarounds that you have to do, but you bypass an entire set of perspectives that may have nothing whatsoever to do with what you're trying to do, and they might even be antagonistic to it. So these guys did a lot of wonderful things. Like this is a narrow gauge railway that was on every floor of the Empire State Building. They also built twice as many elevators than are there now, just as temporary elevators, but going up 85 stories in order to move equipment around. And when they got the building up, they took down these elevators. Sounds ridiculous, right? Not really. Now, the other thing about engineering, real engineering, that makes it rather different still from what we attempt to do in software is this problem. This is the Tacoma Narrows Bridge. We have much of our infrastructure is crumbling. Here's one that wasn't as funny as the Tacoma Narrows Bridge was funny because nobody got hurt. It was predicted by a University of Washington professor, and the reason they got good movies of it is he said when a wind comes up that's over 55 miles an hour, this bridge is going down. And so when that wind came up, they went down to a now famous camera store in Seattle, famous for supplying the movie cameras, which they then took out to the bridge, set them up, and watched the thing shake itself apart. This one, though, in Minneapolis was not so funny because many people got killed and a whole school bus full of children just missed getting demolished. And so there were many casualties on this. And the trace back on this one was, first they thought the rivets were substandard, but they turned out to be right. And they finally found out that those gusset plates, those square things that the rivets are joining those beams with, by a clerical error, were about 3/8 of an inch, not 3/16 of an inch too thin. And 20 years later, that defect in the structural engineering plus the clerical error brought down the entire bridge. So the point here is that one of the reasons you can fly in a jet plane and not feel upset, and if you knew what was going on in the jet engine that's right outside there, and you should if you aspire to be an engineer, you will know that inside that jet engine there are temperatures that are higher than the melting point of any of the materials in the jet engine. It's just one of those great things. But jet engines run for thousands and thousands and thousands of hours. They're one of the most perfect engineering creations, especially given the difficulties that they labor under. They have to spin at 30,000 RPM. They have these temperature problems. They have enormous shear forces and everything else going on. They're just fantastic. So the thing that has allowed engineering to advance is that people get really pissed off when their friends and relatives wind up dying on some engineering failure. And so the forces of nature plus the social forces have conspired to make engineers rather careful. And of course, if you think about the parallel situation inside of a computer, the forces and the masses are slight. So many software systems are starting a crash that will take 10 years to happen from this instant they are actually deployed. They're completely buggy, but the gusset plate is going to take a long time to gradually come apart as it gets more and more complicated. And so when you move from something where you're doing something out in the world of forces and masses into a world where you don't have these, you have to have an artificial sense of discipline. This is something we are still learning how to do. Now, we don't know what happened to the Roman engineers who failed. I suspected, because their engineering was so good for its time, that I've suspected that they actually wound up in the Colosseum for failures. But consider this. This is the longest extant. It's not the longest Roman bridge ever made, but it's the longest one that we still have with those light poles on it, because it's been in continuous use for over 2,000 years. And has had cars running on it for the last century. If you go look at this bridge, it's in Merida, Spain, near the Portuguese border. It looks like it was built yesterday. This is partly because the Romans created the best cement the world has ever known. It took a long time for us to find out, just really about 10, 15 years ago, to find out exactly what the secrets were of the Roman cement. And how about this one? Same age. Again, if you walk right up to it, it looks, holy smokes, this thing looks like it was built yesterday. If you've ever been to, how many people have ever been to the Pantheon in Rome? If you've been to Rome, you've been to the Pantheon. First time I went, I thought, wow, it looked like it was made out of granite, and then I found it was made out of reinforced concrete. How many people, most people here might have found that out. Did you realize? How many people realize it was made out of reinforced concrete? Looks like it was made yesterday. You go around, it's just nothing is crumbled. Just incredible. So if you really care about it, engineering goes from being a set of these principles to a true art form. And you could even go so far to say that the big art forms of the 20th century were science and engineering. That's a lot to live up to for something that wants to call itself a science like computer science and wants to call itself an engineering discipline like software engineering. Yeah, so the answer to this question is no. Software engineering cannot do anything like this today. And to make some comparisons here, I just note that a 400-page book has 20,000 lines of text in it. Each one of those could be a line of code. So a 20,000-line program is one 400-page book. And a foot of books is about 300,000 lines. Million lines of code per meter. There's an easy one to remember. And the Empire State Building is about 441 million lines of code high as stacked books. It's 20,000, 50 lines of code at a time. Stacked up, that sounds like a lot. But in fact, a lot of companies are wrestling with about this much code. Personal computing, which I had something to do with a long time ago, Microsoft's essays into it provide operating systems over 100 million lines of code and application suites of well over 100 million lines of code. You look at that, you think, are we really getting that much bang for a couple 100 million lines of code? I hope you're saying no. I hope you haven't gotten complacent about this. So personal computing, 200 million lines of code. But of course, it's not really that much. The problem is that when you make a lot of code, there's a point where the dependencies are so intertwined, the engineering has been done so poorly, that people start becoming afraid to remove things. So they just let it stay there and they start layering over it. This big software company has now gone over 400 million lines of code. I haven't changed the slide. And I used to use this analogy because, I mean, a pyramid is kind of a garbage dump plastered over with limestone, so it looks nice. It's just a big accretion. But when I looked at this picture, I was thinking, I can't use that metaphor anymore because look at how modular these pyramids are. We would love to have that modularity in the code that we write. So I think the picture that fits our code better is a slum, particularly the web, but basically it's all rather slum-like. There's no large sense of architecture of any kind. Things are tacked in there. Urban renewal bulldozes out some stuff, but just leaves the stuff lying around, never carts it off, and so forth. So the real question is not whether we can improve on this, but what is the actual level of improvement, which is tantamount to asking how complex is the actual problems we're trying to solve compared to the complexity we're creating by just bumbling around. So now let's ask a question about what science is, now that we've talked about engineering. So real science looks at hairballs. This is my favorite hairball. It's about this big, recovered from the stomach of a woolly mammoth found in a glacier. But because hairballs are ugly to look at, but it got your attention, especially when I say how big it is. And it represents complications, but the universe is good enough. The starry night, it's prettier, but it's still complicated. People spent thousands of years misunderstanding it in a bunch of ways. And we little creatures with our brains have languages, and we can make all of our languages out of the Sheffer stroke here. This is the NAND operator. And because we have tiny little brains, we invented mathematics, and we can come up with something like Maxwell's equations or Heaviside's version of Maxwell's equation and put a large part of the phenomena that we're looking at out there on a t-shirt. And this represents complexity. So the complexity of the electromagnetic field in large amounts of it, enough to invent radio and radar and et cetera, can be represented by a couple of these equations. And these equations should be symmetrical because the magnetic field and the electric field are trade off against each other, but they aren't. So if you worry about that and you happen to be named Einstein, you will come up with the special theory of relativity, which will put symmetry into the whole thing, and you get down to two equations, just like you should have, one for the electric field and one for the magnetic field. Now, science is not this. So the problem is when most people take science courses, they're taught the t-shirt. But science is actually that. Science is the realm of the relationship between the phenomena that we can't get to. And similarly, we can do science with engineering because it's an artifact, it has phenomena. So we can actually look at that bridge that we built there, and scientists can look at what engineers do and make a t-shirt of it. So we have t-shirts of what bridges are, their theories of bridges. And then the cool thing, this is why it's great to be alive today. The cool thing is you can take that t-shirt and make one hell of a bridge. So engineering was around for a long time, but it didn't hit its stride until it had the yin and the yang here of making things and looking at them the special way that science does. And how big is this bridge? Well, see those little boats down there? Those are super tankers. So, just for comparison, there is our Empire State Building. So the pylons on this bridge are the height of the Empire State Building, and there's the Great Pyramid of Egypt. So this is the Asahi Bridge in Japan. Just can't beat it. So lovely. And so this is what we want to think about. We want to think about real engineering. We want to think about real science. Computer science is not real science. Ask anybody to give you a definition, they'll give you an engineering definition. And part of it is because computer science persists in only building things. It doesn't spend a lot of time trying to understand them. So you can look, computers were built. They're complicated artifacts. Programming languages are complicated artifacts. You can do the same thing. John McCarthy looked at them, and being a mathematician, he wanted a t-shirt. So this is the programming language Lisp on a t-shirt. And once you look at that, you realize, whoops, programming is not as complicated as I thought. All the semantics I really care about are not in these humongous Fortran or Java compilers, but they're actually very small. And when I make them small enough for my tiny little brain, I can actually think about them, manipulate them. Whereas trying to go over on the other side and mess around with Fortran directly to make it better, it just never happened. So John came up with a mathematical theory of computation. And those of us who came in the next generation after McCarthy got to do some really fun things with this idea. Now I should mention that what I'm talking to you about actually happened in the 60s, and it bore some real fruits. But in fact, it never made it into the world of the 60s, which was dominated by IBM, or the world of the 80s and 90s, which is dominated by Microsoft. It just didn't happen. So most people program in a way that is strikingly similar to the way programming was done around 1965. So let's take a look at the idea of tactics versus strategies. The simplest thing when we have materials is to think tactically. Have a bunch of these materials, piles and stacks. Simplest things we can get out of those, hardly any design effort at all, is pyramids and walls. And people did this with bricks for thousands of years before somebody had a strategic thought, which is, hey, let's make something out of the bricks before we make the thing. Let's make a new kind of building component that has a different kind of structural integrity than a pyramid does, and all of a sudden we can kick ass. Took thousands of years to get beyond what the brick forced into our minds by being in front of us to this very odd thing that requires more building materials to make than you have when you're done. This is one of the hard things about an arch. It's hard to imagine it because it doesn't work until it works. So people just ignored it. And the same thing happened in computing, where we build things out of the NANDs. Basically, computing is all about comparing things. So you can take materials, like even two rulers. This is something that first graders love, is they can do any fractional arithmetic problem their 10-year-old brother can't do, and they can do it in 2 seconds with two rulers. Right? Because a ruler is an addition slide rule. You show this to a kid, they'll love you for life. Just compute the whole thing out ahead of time and say, here's what it is, and by the way, you're teaching them vectors at the same time. And so it beats regular fractions in many, many ways. And of course, the Romans and the Greeks, Romans had a socially accepted QWERTY form of numbers called Roman numerals, but they didn't use them. Most people use this the wrong way. The Romans and the Greeks had abacuses to compute with. This is a Roman abacus, and those stones are called calculi. The calculus came from this notion of, it's what they pull out of your teeth also when you go to the dentist to get the plaque removed. They call them calculi. And flip-flops didn't come about because people wanted to do computers, but because a couple of Brits wanted to see if they could make a memory that could do some of the things human memory could do out of materials. Because remember, vitalism was a big deal back then. And ENIAC. But the problem is matter is inconvenient for this. It just, basically the scaling problems overwhelm you with very little return. So you need to go strategically. And of course, this was done a long time before with the Jacquard loom, von Neumann architectures, von Neumann style programming languages, and even the programming languages of today like Java, which is also a von Neumann style language in spite of a few trappings it has on it. And basically, the programming that we're doing today has not stirred from this in 50 years. There have been about 3,000 different programming languages invented, and some of them really useful. But the style of programming that is used today is almost entirely this style. And it's a style where the programming language is rather similar to the underlying storage mechanisms and control structures of the machine. There are a few conveniences there, but not a lot and not enough. But, of course, there are always weird people out on the fringes who, like Turing himself, who did things that were completely different. For instance, Sketchpad, which is having its 50th anniversary this year, you programmed it by putting in constraints that Sketchpad had to figure out. So instead of writing solutions to problems, you just gave Sketchpad what the nature of the problem was, what the nature that would characterize a solution, and Sketchpad had 3 problem solvers. And in 1962, it would solve those problems for you. By the way, he also invented computer graphics while doing it, and also this was the first object-oriented system I know of. So those 3 things were done by Ivan Sutherland as a thesis project in 1 year, 1 person. And I once asked Ivan, how could you do these 3 things in 1 year? And he says, well, I didn't know it was hard. Now, Ivan is a genius, but he also had the advantage of just aiming for what we really needed. He didn't worry about whether it was hard because nobody knew what was easy and hard in 1962. He just went for what we needed, which was an interactive system that you could show sort of what you wanted, then tell it what the criteria were to finish the job up, and it finished the job up. Great. Too bad we don't have it today. The internet, another thing which is almost completely ignored by computer people. Why? Because it works too well. Most computer people, certainly most people in the world, but most computer people don't even think of this as technology. It's completely different from the technology they're used to. The internet has never gone down. It started running in '69. It's been up continuously since then. It's replaced all of its atoms and its bits without ever being shut down. People are shutting down their software systems all the time. They shut down individual servers, even though a server is just a name. You never have to do that. So what we've got is 2 cultures here. We've got a culture that was able to make something that scaled successfully by 11 orders of magnitude. And we've got another culture who can't even appreciate the feat of engineering and science that took to do. So the internet is really the only extant true object-oriented system in the world right now. And then there's, of course, AI, which people have lost interest in, just as it was starting to get really well worked on. So we should be spending more time thinking about this. Now, one little blast from the past. 1973, we showed this machine and this system. Notice the overlapping windows there. It was a view-oriented, object-oriented system. Desktop publishing was essentially the views without the borders on them. These got split up when they came out into the real world, but at Xerox they were one thing. There was no operating system because you don't need one. Okay, and so when Xerox asked us what we were were doing, we gave them our own version of Paul Starrett's speech, not even a pick and shovel. So part of the deal at Xerox PARC was we built every bit of the hardware and software ourselves from scratch. So we did not go out and buy commercial computers. We did not go out and buy commercial software. And the reason is this stuff was so different that we would have spent all of our time running into walls that were simply irrelevant to what we were trying to do. And then the cool thing was this was a tiny machine, 128K RAM, and we used half of it for the display. So it had a display about 800 by 600. And all the software from the end user down to the non-existent operating system, down to the metal of the machine, was only about 10,000 lines of code. And it was done in a language we invented specifically for the purpose. So one way of thinking about this is, in the end, no matter what it is you think you're doing, math wins. The thing that is math, the mathematization of an idea, dominates all other things once you've done the spade work around the edges. At some point, you have to sit down and do something like mathematical thinking in order to collapse all the things that seem to be artificially dissimilar into things that are similar. This is called making an algebra. And this was a technique that we use pretty generally at PARC. And so in a few years, we did this, the bitmap screen, the GUI, WYSIWYG and desktop publishing, real objects, laser printers, Ethernet, peer-to-peer and client server, and about half of the internet. Now what was interesting about that, perhaps, is it was only 24 people. Any company here could have afforded to do this. 24 people, just $10 million a year in today's dollars. You could do it right now. You won't do it, though. Nobody is doing it. You won't do it. In spite of the fact that it returned 30+ trillion bucks. It's returning about $1 trillion a year still. So this is a huge win, but in fact, it is against what most people think is good practice. And I don't mean in computing only, I mean in management. Okay, so we'll leave that because we don't want to talk about the past too much. But most people do not realize it was only 24 people. That is only 4 to 5 years to do all this stuff, and doing it all from scratch. Okay, now let's take a look at a science project in the present. Same idea here. So all of these ideas I've been talking about here, we're going to apply them to this big thing called personal computing. And it's got all kinds of stuff in it. So again, we're interested in this area that goes from the end user all the way down to the metal. So this is a lot of stuff. We want to know how many t-shirts does it take. Right, so this is a completely different thing here. We are not interested, we're doing science here. Now we're going to have to do a little bit of engineering because the only way we can validate this science is by making it run. But this is a science project. We want those t-shirts. So let's take a look. So let's say half of what Microsoft or more has in there is just code they can't get rid of. But still, most of these, Linux and OpenOffice and stuff, it's like 100 million lines of code. So it's a lot of stuff of different kinds. And so now here we have we're kind of behind the 8 ball of having a brief talk. So to do this part in a reasonable way would take a couple of days. So and I hate bullets. So please do not regard these as bullets. Just look, there are 10 blobs out of 12 or 13 blobs that we used. And what they are things, a couple of those we invented, but most of them were things that have been around for 50 years that didn't make it into the particular design culture that computing is. See, the difference here is nature helps physicists be honest. Because in the end, you're supposed to submit your theories back to nature. But the problem is we're a design field. So our trade is bullshit. That's what design is. And there's good and there's bad and there's indifferent. A lot of stuff in between. And so we can have a fad, like for instance semaphores. Semaphores were known to be a bad idea when they were first invented by Dijkstra and Hoare. But in fact, in that culture, they took on, and for a variety of different reasons, they are still being taught today and they're still being used today. Why are they a bad idea? Anybody know? What's wrong with the semaphores? You got system lockup. And there is no way to do something ahead of time that will tell you you won't get system lockup. So this is like the world's worst idea, to let the CPU control the time base of your computations. You're screwed. May take a while, may happen quickly, but it's just basically a bad idea. And there was already a good idea, also thought up by John McCarthy in the early 60s, that actually works and works much better. But it's just not generally used, and it won't be used for a while. Because these things take decades to get rid of things that are, de facto religions. So I'm just going to pick on a couple of these. I already talked about math wins, and I want to talk about this now in this area up around in here, because one of the things we have to do in personal computing today is make anti-alias 2.5D computer graphics. And we have to make it look really good. And if we didn't have it look really good, then we would be sloughing off part of making something that is like computer graphics that we can recognize today. So, and of course, whenever you have a hard problem, you get a graduate student to do it, because they are just so much smarter than we are. This is Dan Amlang, who's a graduate student at UC San Diego. Very good mathematician and computer guy. And even better, he has a mom. Of course, we all do. But his mom happens to be a high school geometry teacher of that special kind that actually understands math. And so they do exist. And so he went home Thanksgiving 3-4 years ago, and his mom said, "Well, son, what are you doing at Viewpoints?" And he said, "Well, I need to reduce the amount of code to do computer graphics on a personal computer by a factor of 1,000. And she said, "Oh, that sounds interesting. What are you going to do?" And in fact, her expertise was in projective geometry. So Dan did not come back from Thanksgiving. He stayed working with his mom. He and his mom worked together on this thing through January. He finally showed up in January with this formula. And so this is one of these serendipitous things that you can't completely supply by method, but because this stuff has been kicked around by the best people in the world for 45 years. But in fact, they found a new way of thinking about the involvement of an arbitrary polygon with a pixel that computes exactly the right shade of the pixel to give you perfect anti-aliasing. And it's only that big, and the next thing Dan did was to make a language out of the mathematics that looked like the mathematics but could run on a computer. And when you tell these 45 lines of code to do it, they can do things like this. They can render anti-aliased text and anti-aliased graphic objects. So that was a great start. And this language that he devised, he decided to make it a data flow language with kind of functional engines at the nodes. And because of that, it is highly amenable to automatic use of parallel resources. So here's one of our benchmarks. So this is 5,000 anti-aliased translucent characters being re-rendered every time by these 45 lines of code. So there's no caching or anything here. And we can take a look at the CPU usage. And we can see that it's basically using, so this is a 4-core Mac, but the cores can handle 2 highly interleaved threads at once. So you're seeing that one of those is being devoted to this task, and the fan has come on. And as I say go faster, it says, okay, give me another thread. There it is. And what it's doing here is, when I say up to 4 here, it's spacing them out so they're each in different cores. And as I go faster and faster, it starts interleaving them. And I can start zooming in here so you can sort of see what's going on a little better. If you got enough monkeys. Yeah, so we're actually quite surprised that this is a lot of computing, but we're getting a lot out of it. So our thought was, wow, we should be able to make a whole system just out of this math. And so this is, in fact, what I'm using. So I'm not using PowerPoint here. It's probably obvious by now, but here is this system that is this replacement for personal computing, and here's my next slide, and here's Dan's brother, and here's all the compositing rules. And so, for instance, here's this one is invert. Here's another combination rule here. So it's 95 lines to do all of the compositing rules that you use. So now that you've seen, and of course there are those 45 lines. There's gradients. So I should actually, now this user interface here is made out of this system also, because it's all one big desktop publishing document. And the system is also live. So this has not been compiled away into C code down there. So I'm actually going to pick an object here like this menu here, and I'm going to say, oh, okay, let's change the gradient fill on this. And yeah, something like that maybe. Or maybe we don't want as hard an edge, so we'll zoom this out. Okay, get the idea? So the whole system is live. It's using its own stuff here. And as we keep on chugging along, we can see here's pen stroking, filtering. And so all of the graphics for personal computing in this little science exercise came out to be 457 lines of code. How do we know it was 457? Because you can count 457 things. Right? It's hard to count 400,000s or 40 million or so on. So this is about 1,000 times smaller than the way it is done, say, in Firefox. Right? So 1,000 should get your attention. Right? You have to learn a new language. On the other hand, here it is. The whole thing is just a few pages of code, and it's live, and you can run and use it. Okay, so now, of course, where did this language come from? I have to build that. And so there's actually quite a distance between one of these compositing rules, a one-liner of code, and getting the result at the other end. And so I need to remove the hood and show you what's there. And this looks a little more daunting, because I have to translate this language into a standard form. I have to translate this into another language that is sort of like C. I have to translate to something that eventually will run on the 86 architecture that's on this machine. That looks like a lot of work, and of course the system runs on multiple processors, so I have to do that. And so one way of thinking about it is, gee, it looks like there's a lot of work in these square boxes here. And so we need another special language. So we've just showed you a domain-specific language. In the old days, they were called problem-oriented languages. I like that old terminology because I'm old. And so we need another problem-oriented language here whose problem domain is transforming languages. And of course, there are tools around for doing this, but this is one of the big stoppers for people doing this themselves, is making a language the way it is taught in school is a daunting procedure. It's usually taught through some set of tools like YAC. This is not the way to do it. But the poor student comes out either not understanding it all or convinced that it's too hard. But in fact, you can make a much better language. So here's one we did called OMETA. And here's a simple arithmetic expression. And here's the program. And if I say do it, it transforms that expression into a tree. And if I come down here and pick this more complicated expression up and paste it in here and say do it, I get that. And so this translation system isn't just for translating things that have strings. It translates any kind of objects into any other kind of objects. So you want to do it in that generality because you're going to use this everywhere. And so this graphical language winds up being 130 lines of code to make the trees and another 700 lines of code to make the lower level stuff that is actually run on the machine. So you could say, 1,000 lines of code, 900 lines of code to make that graphical language. But this is like a shaggy dog story, right? Because, well, now I have to make the language transforming language. But of course, it can make itself. And Alex Warth did it particularly nicely, so it can make itself in 100 lines of code. And as you get closer and closer down to the bottom of the system, you start using these base things over and over again, and the problem-oriented languages stay on the top. Okay, but we have to do the internet. So TCP/IP, 20,000 lines of C for that. So one book, one of those books. And this C code on most computers is a good, nice job. And TCP/IP was invented by experts. And so we didn't expect to get a factor of 1,000 on this. Ian Piamarta only got a little more than a factor of 100. So TCP/IP is about 160 lines of code using these techniques. And if you're interested, this is particularly elegant the way he did it. I'll explain it later for people who are interested. So this represents taking something that was done by very good people but in the wrong language and done essentially in a way that generated unnecessary code. The big key here was not so much the language as the method. The method came first and then we did the language to do it, and so the whole thing collapses down. Okay, let's take another one of these metaphors, particles and fields. Everybody understands this as a kind of a metaphor for iron filings in a magnetic field. The iron filings seem to know what to do. They're feeling this field and they're doing individual things that look like they're somewhat coordinated. And in fact, there are animals that do this also, like ants. So here's a little ant simulation. This is their nest. These guys are their food. And if we start this thing going, then we see that the ants are finding the food, going to the nest, and they're leaving this pheromone trail. So this is using about 11,000 parallel processes, because each little cell is being used to diffuse the perfume the ants lay down. And you see right now all of the ants have been captured by the field even though they're not communicating directly with each other, they're communicating indirectly with each other, and we would call this loose coupling. Well, if you have crazy brains, you could imagine that a paragraph of text is one of those things. Who said you could do the encyclopedia over here? Thank you. Because we're not going to do the encyclopedia, but we're just going to say, hey, you should be able to organize these little ants to do a paragraph. And so the simplest thing that you can get fifth graders to figure out is, well, when you have to do something, follow the guy who's in front of you, and if there's nobody in front of you, go to the upper left-hand corner. And if you find yourself over the right-hand margin, tell the guy in front of you, and eventually somebody will know what to do, like go to the next line. Right? So let's just say, go do this. So I just gave you like a 3-line formatter. Right? So this is math. I'm going to set it off again. And I'm going to point out that I can edit this. Let's let it, so I can turn general here into justify. And it's just redoing this over and over again. Right? So the editor is actually working. Okay? Now, another way to do it's a little faster is to say, hey, don't follow the leader here, because this is just for the crowd. When it's time to do your thing, wait until the guy in front of you gets to the right place, and then go right behind him. So this is called jump, and here's what that looks like. So now they're all standing still. Okay. And so if I start jump here, and I just say, now do this in between frame times. Bonk. Okay, so all of the editing here is done like this. And in fact, this is another one of the documents in this universal document system. Remember, we have to do Microsoft Office here. But why would anybody in their right mind give you 7 applications that all do almost the same thing, but not quite? Well, the answer is simple, because amazingly, people will put up with this silliness enough to buy it from them and thus encourage them further. This is nonsense. Really, what you want is a universal document and just different ways. Really don't need to have a different system for the World Wide Web, do you? No, because it's just a different way of accessing these multimedia documents. So this is actually how we write code. So this is an explanation to somebody like you to show in a little essay how the code actually works. So we start off here and say, okay, the first thing we want to do is just get these guys out there randomly. So these 2 lines of these 2 little boxes of code do this. And here's one that just does this without worrying about the next line. And here are some special cases. So this is reminiscent of the way Knuth sometimes likes to program. So you actually learn the thing while you're looking at it. You can do little experiments, and by the time you've done that, bingo, you've got the thing. And so here this is yet another problem-oriented language, but with rules this time. So rule-based. So 7 rules for doing the layout. And the whole editor, like Microsoft Word, paragraphs is 35 rules. Okay, so that's all you have to do for that. Okay, here's another area. So a thing that's very useful to have is problem solvers. But the problem with problem solvers, and these problem-oriented languages are problem solvers. They aren't integrated. So you wind up with a hodgepodge of different things serving different things, and you want to be able to integrate them. So here we can have a simplex solver, differential equations, propagation, dynamic programming, relaxing, the rules for the paragraph. These all have different problem domains, and what we want to do is to approach them strategically, as I've been talking about here, through general relational languages that talk to a kind of a little operating system for solvers, and often with the help of an expert system that helps make a strategy for using these things. The further stuff here is beyond the scope of this short talk, so I'll just move on here. Okay, here's an important idea. Too many ideas in this talk, right? But here's something that happened in the 60s, except nobody noticed it, except maybe the ARPA researchers and the outgrowth of that to Xerox PARC. And that is that the entire paradigm of computing, because of Moore's law, was going to be able to shift from a gear-like way of doing things, basically tight coupling, brittle code, to something more like ecology, something more biological. And we use these ideas very strongly in the invention of the internet and in the invention of the object-oriented techniques that we used for software at Xerox PARC. And the deal here is you can fix a clock, but you can only make clocks of a certain size, maybe 1,000 gears before they just clash. This is what happens in today's programming. You have to negotiate with the system, and a lot of what growing the old world into this new world is learning what it means to do this kind of negotiation as you add more system elements. So the next little thing is just a couple of minutes of gloss, because I'm getting close to the end here, but I wanted to say something about systems. And three of the ideas here are that we want to control time. I mentioned this a little bit before. We do not want the CPU to control time for us. We want to control time, and we'll do it by simulating our own time. We don't want to have any preferred centers, so we want to have something like the internet all the way down. And we want loose coupling. Now, of course, this has all been done before, again, with networks. And here now we're looking at physical computers on the internet or Ethernet. And ideally, we'd like our computations to be software versions of these hardware networks. Why? Because in most cases, we will need to do load balancing. Sometimes we'll be able to run all of these guys on a single machine, in which case we just have increased integrity and ability to design quickly. But a lot of the time, especially now with mobile, we want to have the same computations able to drift around the network to different kinds of devices. And in some cases, not all of the computation is going to want to be in the machine that is next to the user interface. So if you think of the user interface here, it's basically a set of views of processes that are giving it images to integrate up on the surface. So here's a great thing if you're interested. Dave Reed's 1978 PhD thesis at MIT, the design of an operating system for the internet. Was never done, but we validated it a few years ago at Viewpoints. So this is, what if you want to make a system that is the size of the internet, that is a software system? What is it that you have to do to absolutely ensure that you're going to be that you're going to have what people like to call data integrity always, so that no matter where you ask a question anywhere on the network about anything anywhere on the network, you will get the same answer for the pseudo-time referent of that question. And a working version of a migratory system was done by Jerry Popek. I put this up here because this book was written in the 80s. You can still get it from MIT Press, The Locus Distributed System Architecture. You'll find the entire book interesting. It's just a thin little volume. But the first two chapters are a classic still of the issues you have to think about and solve in order to do this. But again, this has all been done. This is almost 30 years old now, but nobody uses it. But if you were to use it, all applications are now just mashups, right? We don't want applications as smokestacks because we want to integrate. So we didn't have applications at Xerox PARC, and we did not have operating systems. And the current web, which is getting more and more complicated, can immediately get simple except for all the legacy stuff that has been done so far. So here's something that Viewpoints has on its list, but we expect not to be able to solve this, at least in this pass of doing things, and it may be beyond, it may require a much larger effort than a small nonprofit can do. But if you think about analogies to what's happening with the scaling that's going on here, it basically starts looking like a biological ecology. And these have their own dynamics, and they need to be thought about in special ways. So the ability for us to scale to what Moore's law is allowing right now is going to require us to start thinking more and more like this. And we did this to some extent when we did the internet. Like, I have a degree in molecular biology in my misspent youth. And so a lot of the ways I think about this stuff is through tissue biology and how the 100 trillion cells in our body work without having a dedicated center and so forth. But in computing, we have problems of our own that are special. Then the next step beyond this, the best book I've ever seen about it is Minsky's Society of Mind book, which is actually about a model for human psychology. But in fact, it is a very good model for what the internet is going to turn into. Okay, so the punchline here, we've got three main operating systems. I won't say which one is the lemon. And down on the bottom here, our little Frankenstein monster that we made, that I've been showing you today, is less than 20,000 lines of code. So it's worth pondering. We are not using any of the Macintosh software in order to do this demo. And here's, just to kick off, I think I'll just show this slide and then I organized the talk so I can stop now at any place, and I need to in about a minute. But I'll just leave this one thought with you, and maybe we can have a few questions, and then maybe more will happen. I think there's a smaller group question session coming up later. But let's think about this idea. Something appears, and we've got two things about it that are very different. There's news and new. News is the stuff that is incremental to the categories that we already know. Almost every bit of news is a specific parameter into some category that we already understand. So it's this war, that killing, this marriage, that hem size, that, right? And you can get quite a bit of this out in a few minutes. So there's almost no context to news that is not already inside of our own head. New, on the other hand, real new, not news, real new is invisible. We don't have a category. McLuhan said, until I believe it, I can't see it. That is the way it works in the human nervous system. And so news is something that's been going on for the entire existence of the human race, about 200,000 years. It's basically campfires, and this is what we're doing right now. This is a campfire. I'm doing the best I can do in an hour of telling stories in a campfire. But the problem is, new can take 2 to 5 years to get the new categories that you need in order to actually see it. And one of the unfortunate things that happens is that new, when you try to talk about it and people make an effort on it, they usually transform it back into news. So for instance, we did this as a way of boosting mankind. It was all about learning by doing. But in fact, almost everybody in the world uses it only as a consumable device for their own convenience. I would spend $28,500, which is the price of an average American car, for a laptop, if I could, because I know what computers are good for. But in fact, people only value them as much as they value their television sets, and they use them roughly the way they use their television sets. So the big problem whenever something new comes along, like personal computing and the internet, is that people, when they see a convenience to themselves, they recast it back into the forms that they know about. So for instance, object-oriented programming never made it outside of Xerox PARC. Only the term did. We got designer jeans. But designer jeans are just dungarees with a fancy label on them. Thank you. Oh, yeah.